start. There we go. So we need to interpret f of 5, which is just a normal function value, if you will. We don't need that kind of process that we were just looking at because it's not a derivative value. So here that 5 would be the amount in kilograms, and that 11,500 would be the amount of Kenyan shillings. So we can essentially say something like, if 5 kilograms of fertilizer is used, 5 kilograms of fertilizer is used, the average value for maize is 11,500 Kenyan shillings. So that's just the regular function, so we were just putting it into the kind of context of that function that we were given. And now we want to interpret that derivative value f prime of 5 equals 350. Now, usually we'd always have to start by telling them the x value of 5 kilograms. Since I already have 5 kilograms stated in my previous I'm not going to include that part. But remember, if this were just its own interpretation on its own, we'd have to say something about 5 kilograms. Now, I'm specifically going to write it in that step way for this one, specifically because I know what I want to do next, and writing it in the step way I think is going to make it easier for me to explain what we're doing. So that step way, remember, is essentially we're starting at 5 and then we're adding on an extra x value. So I would say something like if 1 more kilogram of fertilizer is added. So if 1 more kilogram of fertilizer is added, well, then we have to tell them essentially what's happening to the y values. So that's going to mean that the average value is going to increase. So just the average value will increase by that 350 Kenyan shillings. And we don't use kind of that rate unit because we're not using the rate way of interpreting. We said something like, after using 5 kilograms of fertilizer, the average value is increasing by 350 Kenyan shillings per year. That would be perfectly fine, but since we're essentially taking care of that, sorry, not per year, per kilogram. Since we're essentially taking care of that kilogram in this first kind of bit, we don't need it. So it's just increasing by the amount of Kenyan shillings. So those would be acceptable interpretations for those. And now in this next part, it says use the statements in part A to estimate f of 6 and f of 10. All we know is f of 5 and f prime of 5. But this is the reason that I wrote it in the step way. If you think about it, this is telling me if I had 5 kilograms of fertilizer and I'm adding on an extra kilogram of fertilizer, getting me to 6 kilograms of fertilizer, then my average value would increase by 350. So essentially what that's telling me is that I can essentially estimate f of 6 by taking my value f of 5 and adding on that derivative value to it, because that derivative value is telling me if I add 1 more kilogram of fertilizer, what my y values are going to change by. So this would essentially come out to 11,500 plus 350, so 11,850. So essentially I used that derivative value to kind of jump to the next value up. Now this would be an estimate. I don't know exactly that f of 6 would be 11,850, but I can estimate based off of the information that I'm given that that might be a decent approximation. Now what if I wanted f of 10? Well, first thing is that I don't want to use f of 6. Okay, whenever you're doing things like this, do not use the numbers you found, only use the numbers you're given. So we're only given f of 5 and f prime of 5. So I kind of have to start at f of 5, if you will. So f of 10, I could estimate this. Well, my only starting point is f of 5. But again, let's kind of think about what that derivative value is telling me, because remember, it's a slope. So that's telling me if I go over 1, I go up 350. Well, now I don't want to go over 1. I essentially want to go over 5, because I want to start at 5 and end up at 10. So I want to go over essentially 5 steps instead of just 1. What that means is I can essentially still add on this derivative value, but I want to add it on 5 times. So I'll just add on 5 times that derivative value instead of just one derivative value. So here, 11,500 plus 5 times 350, which would give 13,250. Sorry, I got a little distracted. So we can essentially use this idea to estimate anything we want. We can even go backwards. Say I wanted f of 4. So let me just tack on one little extra bit. If I wanted f of 4, I could still estimate that. I could start with f of 5, but I'd have to go backwards one step. So I'd essentially want to subtract off that derivative value instead of adding it on. I didn't actually calculate that number, so I'm just going to leave that generically. But so you can go backwards, forwards, whichever way you want. And you essentially just take the number you want, subtract the number you have, and then multiply that many, add on that many derivative values, if you will. So since the difference between 10 and 5 is 5, that's where I got this 5 from. Once my screen catches up to me and you see the things that I circled. There we go. Now that's green. There we go. So the reason we have that 5 multiplied by the f prime of 50 is because there's a difference of 5 between 10 and 5. And essentially here, with this f of 4, there's kind of like a 1 here. So there's a negative 1, which is the difference between 4 and 5. So let me kind of clean that back up a little bit. You know, I'm going to leave that 1 there, just for giggles. So which one of those numbers, not considering f of 4, because that was like a little extra piece, would be more reliable? Well, between f of 6 and f of 10, f of 6 would be way more reliable than f of 10. Essentially because 6 is closer to 5. So we don't actually know what this function is doing. So say our function did something like this, and here's 5, here's 6, and then 10's over here. Essentially what we're doing here is we're actually using, since that slope is the derivative value, it would be the slope of the tangent line. So we're essentially using the slope of the tangent line to kind of approximate where we're at for the function. So say my function looked like this. I don't know it does, but let me just say maybe it looks like this. Then f of 6 would be a pretty okay estimation because it's not exactly, but my tangent line is still pretty close to the function at that point. Whereas if I extended this, tangent line out to 10, my tangent line would be all the way up here, but my function's all the way down here, and obviously I'm obnoxiously off. Now it's possible that the function could have done something to still stay close to that tangent line even farther, and maybe it was a decent approximation. But we don't necessarily know that because we don't know what the function's doing. So essentially, this idea, while you can technically use it to approximate any number you want, it's really only decent for numbers close by to the number that you have to start with. So if you don't have, if you have 5, anything past, I'd say even 6, but past 7 is going to be pretty far off depending on what the function might look like. Excuse me. So while you can do them in general, just keep in mind that it might be really far off. So in part B, we used that derivative value to estimate values past 5. And like I said, you could also go the other way. This is called tangent line approximation. Tangent line approximation. Because essentially, as I just kind of said, the slope that we're using to be able to estimate these values is the slope of the tangent line. So we're essentially using the values of the tangent line to approximate the value of a function. And again, that's only going to be good for so close. But that's why it's called tangent line approximation, because that's essentially what we're using. We're using the tangent line. You just might not recognize it. It's sometimes also known as local linearity. I will rarely say local linearity, but in case you see those words somewhere, that's what it'll mean. Now, if I wanted to state this in general, essentially what this is saying is if I want some f of x, I start with some f of a, and I can add on the derivative value for a, and I just have to essentially multiply it by whatever my change in x is. Now, we do need to be careful here, and there's probably a better way to write this, but the way I'm going to write it is want minus have minus, no. Why am I suddenly questioning it? No, it's want minus have. Want minus have. Again, there's probably a better way to do that with generic actual symbols, but I think that gets the point across a bit better because you want to be careful with the change in x. Let me reshare just in case. There you go. Should be able to see it now, Ty. Cool. Yeah, just let me know if you ever can't see it. Sometimes it bugs out. What am I saying? Want minus have. So we need to be careful with the change in x because if it needs to be the correct sign. So if we're going backwards, we need it to be a negative, and if we're going forwards, we need it to be a positive. So we need to make sure that it's not just, the larger value minus the smaller value. It's what you want minus what you have. So if we have 5 and we wanted to find 4, we would have to take 4 minus 5 to essentially get that -1 that I was using up here. So you do want to be careful with that. But anyway, that's the generic format for that. So this type of idea is essentially what gives us the tangent line. Now, we have talked about the tangent line already because I wanted to say the word tangent line, but this is kind of officially where it comes into our notes, is this section here. So this is what gives us the tangent line, and it's an equation that we can use to estimate any value. But again, as I've kind of stated already, the farther you go out from the starting point, the less accurate the estimation. Do y'all hear that, or is it just me? Am I going crazy? What is happening? There is a strange sound in my office. Hopefully y'all can't hear it. It's not my fan. I don't know what it is. Anyway. So, now we're going to define things I've technically already defined, but again, this is kind of where they formally come into our notes. So just a reminder of what they are again. If we have 2 points on a function and draw a line between them, we're going to have a secant line. And then the line that touches the graph of a function exactly at one point in a small interval is, of course, our tangent line. And let me just do a quick little drawing of what those would look like. I know we've already talked about them a lot, but formally, this is where they're presented in your notes, in your book, I should say. And then secant line, just pick any 2 points you want. Pick different points. This one and this one. So just a reminder about what those are. So I'll leave that up for a couple more seconds so people can get it down. And then we'll do one more thing in 2-3, and then we'll head over to 2-4. Boy, that's annoying. All right. So we've talked about tangent lines a bunch, but we've never actually found what they are, and that's what we're going to do now. Now, I wrote this down. I'm still on green. I wrote this down in a way that you'll be able to refer back to it later, because at this point in time, we kind of have to, so we've been finding derivative values, but we haven't found like official derivatives. So We've had to estimate them using instantaneous rates of change. And possibly by the end of this week, but definitely next week, we'll get into some ways to find actual legit derivatives without having to estimate them. So this process is kind of written with that in mind, the fact that you can kind of come back and look at it again when we have those. So it might be phrased slightly weird, but hopefully it'll make sense. So the first thing we want to do is we want to find the derivative. So in our case, I'll put value in parentheses because that's all we can do at this point in time. But again, you can kind of come back to this process later and it'll hold for what we cover next week as well. What you're going to do is well, first of all, we're taking the tangent line at A. So when I say A, that's why we're using A, because we're asked to find the tangent line at A. So you're going to take that value A and you're going to plug it into the original function. This is going to give you your point. And you're going to plug it into the derivative. In our case, we're just going to use the value. And that's going to give us our slope. Because remember, essentially the tangent line is a linear equation. So we need two things to be able to write a linear equation. We need a slope and a line. A slope and a point to write the equation of the line. And then we use that kind of linear equation process back from chapter 1 to write the y equals mx plus b. So let's do one of those. So let me try to just scroll down a little bit. There we go. Find the equation of the tangent line to the equation x squared at x equals 5. So the first thing we want to do is we want to find the derivative. So in this case, we'll find the derivative value. Now at this point in time, we have to estimate that using our instantaneous rate of change. So we have to estimate using our average rate of change. So we have to use something like 5 and 5.001. So we'll have f of 5.001 minus f of 5 all over 5.001 minus 5. Take as many decimal places as possible. I'm missing a 0 right there. Let me rewrite that. What's that? So this will get you about 10.001. I could make my life easier and round it to 10, but I'm not going to. Just because I want to be difficult. So we're going to keep 10.001. And that's going to be the slope of the line that we want. So now I need to take that a value of 5 and plug it into the original function. How did I actually write a? So we have 5 squared equals 25. So that means we have our point of 525. So now that we have our slope and our point, we can go ahead and write the equation of the line. So we want y equals mx plus b. Well, we can use them to find b. That's what I mean when I say that, but I realize when I say we can use that to write the equation of the line, you might think we're done. So we got to find b first. Subtract the 50.005 from both sides. You get negative 25.005 is equal to your b value. So then you know that the equation you're looking for is 10.001 x minus 25.005. And this would be your equation of your tangent line. questions, concerns on how I did any of that? Or anything else in 2.3 before we head over to 2.4? All right, I'll leave this up for like 5 more seconds. In case someone, oh man, I meant to fix that. Dang it. All right, so jumping over to 2.4, which is a very short section, and since this isn't lagging as much as I thought it would be, we might actually finish 2.4 today, but we'll see. Come on, zoom in. Now, there was a typo that I meant to fix between my 2 classes because I noticed it in my last class, but I didn't have enough time. Is that one of these in each case should be a less than, should both be greater than. I will fix that and put up corrected blank notes, but in case you're using them now, that was an unfortunate typo. So 2.4 is called the second derivative. So since the derivative is itself a function, we learned that in 2.2 where we had that really awkward Desmos that I had to keep switching back and forth between. So we defined the derivative function in that section. So essentially, if the derivative is a function, we can also calculate its derivative. So we can essentially take the derivative value of a derivative value. Well, really a derivative of a derivative. Anyway, so if y equals f of x, then the second derivative which is notated by f double prime of x, which is how you would read that, f double prime. Or we could also write it in Leibniz notation. So side note, remember Leibniz notation looks like dy over dx for a regular derivative. For a second derivative, if you're curious, we don't use it very often, but if you're curious of what it would look like, it looks like this, dy squared over dx squared. Yes, my squares are in the right spot. I could explain why it is that way, but I don't think anyone cares. We will use pretty much just this notation for the second derivative. For the first derivative, we kind of bounce back and forth every once in a while between Newtonian and Leibniz. But with the second derivative, we usually just write that f double prime of x. So the first chunk of this section is just a lot of notes and definitions and just recalling some things that we already knew and revamping them a little bit. So remember from essentially 2.2, we had that kind of set of notes that I've circled about 5 million bajillion times and told you it was going to be really, really important. We're going to build on that right now. So if the first derivative was positive on an interval, we said that the original was increasing. And if the derivative was less than 0 on an interval, we said that the original was decreasing. So kind of notice what's happening here. We're starting with a derivative, and we're kind of going backwards to the original. So say I started with the second derivative. If I wanted to start with the second derivative and say the second derivative is positive, if I follow a similar pattern to that, if I kind of go backwards one step, if you will, then I'd have f prime. So if f double prime is greater than 0, if f double prime is positive, then the original derivative, the first derivative, is increasing. It follows that same pattern. And if the second derivative is negative, then the first derivative is decreasing. So if the derivative is increasing, the derivative is a slope, so that means that the slope of the original is increasing. So it's going to bend upwards, the function. The slope is increasing, that the function is going to bend upwards. And if f is decreasing, the slope is decreasing. So the function is going to bend downwards. So if you think back, you might remember maybe that way back when in chapter 1, we defined some things that were essentially when the function was bending upwards and when it was bending downwards. Concave up, concave down, coming back. So we have, if the second derivative is greater than 0, then the original function is going to be concave up on that interval. And if the second derivative is negative, then the original function, that looks weird, then the original function is going to be, what am I writing? Concave down. So we have all of these relationships between all these different types of functions and derivatives and second derivatives now. And I'm essentially going to take everything we just wrote down and write it again in this kind of summarized table. I would suggest committing this table to memory. I cannot tell you how often it is used and how often you need to use these relationships between these types of functions. And it's just easier if you can just remember the table. So essentially what we have, again, I'm just essentially rewriting everything we just wrote down, but in a more concise way. If the original function is increasing, then the derivative is positive. And if it's decreasing, then the derivative is negative. Just from that information, we can't say anything about the second derivative. Let me pause for a second. Gotta remember that some of y'all are writing this down as we go. So essentially what we do now, well, a way to maybe help you remember it, it's not really that you have to write it down in this way, but to maybe help you remember it, is essentially this pattern kind of just shifts over. So if we have that the derivative is increasing, then the second derivative is positive. And if the first derivative is decreasing, then the second derivative is negative. So it's like that same idea, just with kind of shifted over a little bit. And this is where we have a bit more information because we were just told if the second derivative was positive, we have concave up for the original. And then concave down if the second derivative is negative. So I'll give you a few seconds to get that down. Again, highly important. Highly suggest committing that to memory, or at least being able to know how to write it out. Because there are so many things that we're going to have to pull relationships between different sets of these. All right. We kind of wrote this down the last time we talked about concavity, but I want to do it again because we also now have a few new details. So at this point, we're mainly focusing on visuals for concavity, and we're still going to have to do that for a little while longer until we get to some of the calculus techniques to actually find it. So remember that this whole piece is concave up. So now we know that if it's concave up, then the derivative, if you will, the first derivative is going to be increasing. And remember, we kind of have these two pieces. We have a choice of f being decreasing or f being increasing, which would mean that f prime is less than 0 and f prime is greater than 0 respectively. So just kind of writing down these extra pieces of information we have now. And then we have our concave down option. So your first derivative would be decreasing. Over the whole entire thing, both of those options, f prime would be decreasing, which is kind of why I wrote them in the middle. But then we have either f is increasing or f is decreasing. So f prime is positive, f prime, or f prime is negative, respectively. So I'll give you a few more seconds to get that down as well. We've only got 2 examples, and that's the end of 2-4, so we might finish 2-4. My other class, we didn't quite finish the last example, so we'll see. We'll see how far we get. All right, a few more seconds. All right. So let's look at these graphs and determine where their second derivatives are either positive or where they're negative. So, we have our concave up and concave down options. And I'll just kind of, whoops. Why do you do this? I'll kind of keep them up here. So if we look at letter A, well, that essentially looks exactly like our entire concave up, thing. So this entire piece through this entire section is all concave up. Because it essentially looks exactly like our concave up, kind of options. So since the name of this function was f, which I point out just because the other ones aren't named f, we would say f double prime of x is greater than, let's look these up so I don't run the other questions. We would say that it is positive everywhere. If you wanted to say on negative infinity to infinity, that would be perfectly fine as well. But essentially just a way to say that that entire graph is concave up. Well, now if I want to look at letter B, that one's a bit more complicated because it doesn't look exactly like one of the 2 full options. Well, if we kind of start going through, it doesn't look anything like either of our concave up options, so that's kind of out. So it does kind of resemble this piece, though. Maybe not fully, maybe it might not look like it's curving quite as much as it should be, but it does, that's the one that it, reflects the most. That's the one that it looks the most like. So since that's a concave down option, therefore this would be concave down everywhere, and it doesn't, change at all. It doesn't curve in any other direction. It just keeps curving in that same direction. So this would be concave down everywhere. So since the name of this function is g, we would say g double prime of x is less than 0 everywhere. Or you could say on negative infinity to infinity, whatever floats your boat. Now in this last one, it actually changes a little bit. And it'll change essentially right here. So if we look at kind of this first piece on the left, which one of these kind of 4 options, if you will, 1, 2, 3, or 4, which one of these options does it most closely resemble? And it's going to be another one of these, kind of 3 options, if you will. So this piece here is going to be down, concave down. But it doesn't kind of continue in that direction. It starts curving a different direction eventually. So we know that it must have changed. So now if we look at this kind of second half of it, well, what piece of these kind of concavity choices, if you will, does that most closely resemble? And that one's going to be essentially this concave up number 2 piece. So that's going to most closely resemble this kind of piece back here. So this is going to be concave up. I should say, I just thought about this right now. Another way to help if you're kind of confused on which option it is, this function is increasing on that piece, right? In fact, the whole thing is increasing, but on the piece that we care about right now, it's increasing, right? But we only have 2 options for increasing, either 2 or 3, if you will let me number them. And between 2 and 3, the only one that it looks like is 2. So you can also kind of split up your options in terms of whether the function's increasing or decreasing and kind of cut your options in half if you're kind of struggling to figure out which one it is. Because each case, concave up and concave down, only have one option for increasing versus decreasing. So if you look at what the function's doing in terms of increasing or decreasing, that can also help you cut down your options. So since this function name was h, we'd have h prime of x is less than 0. on negative infinity to 0. Now, just like with the increasing and decreasing, you get to choose whether or not you put a bracket or a parenthesis. I'm going to just choose a parenthesis, a bracket, just because I feel like using a bracket. It's kind of, so again, it's like that idea of increasing and decreasing. You can't be concave up or concave down at a single point. So we can include it, not include it, whatever floats your boat, and you're still technically right. So we were concave down, so the second derivative was less than 0 from negative infinity to 0. We switched to concave up, so our second derivative is positive on 0 to infinity. Questions, concerns on that idea? So again, at this point in time, we still are kind of, what's the word? That's what I'm thinking of. We're relying a bit on kind of that visual piece where we kind of just have to look at it to see where it's concave up and concave down. We will eventually have kind of a calculus way to find it by hand. But if there are no questions on that, we'll move on to the last thing in 2-4, and then we'll just stop there no matter how much more time we have. We're kind of close to the end anyway. So if we consider the derivative to be a rate of change, which it is, it's a slope, then the second derivative is essentially a rate of change of a rate of change. It's essentially, I'll also phrase it as a rate of change of a slope. So essentially you need to look at how the slopes are changing to look at the second derivative. So say we have this table here. So comparing years to the number of car sales. And the first thing we're asked to do is find the average rate of change for each consecutive interval. So I'm going to essentially make a new table. For our average rates of change, which I'm also going to denote as change in C over change in T. So essentially they want us to do each one of these kind of two pairs. So this one's a bit tedious, but give me 1 second. 80, 1990, 1985, 1995, 1990. Weird right then. 1990, 2000, 1995. I eventually started doing this backwards. Hold on. What have I done? Oh no, I messed up that far back. No! That's okay. 1980 to 1985. 1985 to 1990. Did I mess up? I don't know. Maybe I was just stupid. No, I definitely messed up. 1995 to 2000. 2000 to 2005. Okay. I'm going to do like 2 of these full out, and then I'm going to just tell you what the rest of them are. And if you really have a question on it, let me know. But these are just our average rates of change. So say for the 1972 to 1975, we'd be taking our 1034 minus 587 divided by 1975 by 1972. Let me just triple check that my answer in my notes is right. Is it not? Oh, no, I'm just dumb. So you get 149 from that. And then I'm only going to write out the full thing for the next one, and then I'm just going to tell you what they are. So then for the next one, we would have our 1554 minus 1034 over 1980 minus 1975. Which would give you 104. do the rest of them in the same way, you would find these values. And I'm not going to take the time to do them all in full. Because the more important point of this is part 2. So I'll wait for 5 more seconds in case people are still writing those values down. Wow, another typo. What can be said of the sine of d squared t over dt squared, which is essentially asking for the second derivative? Now, if you think about it, we used the average rate of change to estimate a derivative value. So essentially, these values in this table are estimates for derivative values. So we're essentially going to take those values there to essentially be representing the values for the first derivative. So if I want to talk about the sine of the second derivative, I kind of need to see how my slopes are changing. So if I look at these kind of slopes that I have in this table up here, I start at 149, I go down to 104, down to 7, down to 4, down to negative 50. Come on. Come on, pen. All the way down to negative 50. So kind of in that part there, that entire piece is essentially those slopes are decreasing. Those values are going down. So what I could say, since the slopes are decreasing, so slopes, let me just write some stuff out. So slopes are decreasing between essentially our 1972 to 1995. I know technically those things are ranges, but just for the sake of our sanity, let's just phrase it like that. So since the slopes are decreasing, thus, if slopes are decreasing, so if f prime is decreasing, that means that f double prime was less than 0. So we could say that the derivative, second derivative, the sine of the second derivative is negative. And now, there's going to be a tiny bit of ambiguity here. And that's specifically because we're listing these as ranges, kind of range between two numbers. So I could also look at this table, and I could also say that these pieces in here, notice that there's a tiny bit of overlap there, that these values are increasing. It's okay that I'm starting at the negative 50. That's where there's a little ambiguity because of kind of these ranges. We don't have kind of set values. So we have that the slopes are increasing between essentially 1995, well, 1990, beginning of that, to 2005. And again, I know there's that 5-year overlap, but it's almost like that idea of including 0 and not including in 0 in the thing above here. It's kind of that same idea where we could include it or exclude it, and we're just going to end up including it here. It just seems a bit more wishy-washy because the fact that these are listed as ranges of numbers instead of just one number. But it would be right to say that from negative 50 to that negative 21.4, we're increasing. Wait. No, it decreases again in that last piece. Whoopsies. So we're only increasing from, let me not be dumb, we're only increasing in this piece. And then we're decreasing again. So 2000. Yeah, we're getting a larger negative number, so we decreased. Sorry about that. So thus, d squared c over dt squared is positive. And then I guess technically these two pieces back here are decreasing again. So again, there's that weird overlap. And now you could essentially argue with me, well, you just overlapped all of the increasing. Again, it's still just the fact that these were listed as ranges that is weird. And since the slopes are decreasing again, on 1995 to 2005, the second derivative is negative. I'm going to make a note for anyone looking back at this later. The overlaps are because we're listing them as ranges. So that's the only reason that we have like this kind of overlap going on here. Saying that from -50 to -9.2 that we increased is still correct. Saying that going from -9.2 to -21.4 is decreasing is still correct. Like, even though there's that weird overlap between them, it's just because the x values we're using, if you will, are kind of these ranges instead of just singular points. But the main thing you want to take from this question in the last minute that I have, the main thing you want to take from here is that if slopes are decreasing, then it's negative. If slopes are increasing, then the second derivative is positive. That's the main thing you want to take from here. Is that if you have a table of slopes, wherever those slopes are increasing, the second derivative is positive, and whenever the slopes are decreasing, it's negative. Yeah. Oop, well, I don't know. Let me write the quiz topics in chat. So quiz on Wednesday, it's going to cover 2.2. So you'll have multiple choice, choosing the correct derivative graph. I'm only going to go that way. So I'm only going to do the way where you're given the original function. You have to find the derivative, the one we did 3 examples of instead of just the one. And then it'll cover some of 2.3 where I might ask you to interpret a derivative value and find values using f of x and f prime of x. So what we did today, where we had f of 5 and f prime of 5, and we had to find f of 6 and f of 10, that's fair game. And interpreting the derivative value. I'm not going to ask you to find the tangent line, but those two things from 2.3 and then kind of the idea of the multiple choice questions from 2.2 is going to be what's on your quiz on Wednesday. We're out of time. So we will head over to 2.5 on Wednesday because 2.4 we're done. Although I might glance over your homework because I know 2.4 can give people problems sometimes, so I might glance over your homework and talk about some things from 2.4 before we move on. But anyway, feel free to leave. We are done. If you have some questions, feel free to stick around. Otherwise, I will see you on Wednesday. I'll stop recording now.